So the problem that is fundamental to the information updating problem in a distributed network is the so-called Byzantine generals problem. So what is that problem? Well, there is a city, and in this city, there are two generals that want to attack the city, and they want to coordinate their attack. So the general on the left only wants to attack the city at the same time that the general on the right attacks the city. So what do? Well, what they do is they exchange messages of, we're going to attack tomorrow at dawn. And so the general on the right sends a message to the general on the left to that effect. Now, the general on the right wants to be sure that the general on the left has received the message and is in fact actually doing what he wants him to do. So what will happen? Well, the general on the left has to send a message back and says, I got your message, and yes, I agree, we attack at dawn. Now, the problem is that the general on the left wants to be sure that the general on the right actually received that confirmation message, because if the general on the right has not received the confirmation message, then he wouldn't want to attack. So how can that happen? Well, the general on the right has to send another messenger back and says, yes, I have received your confirmation, and thereby I am now willing to attack. Well, but that's not where it ends, because now the general on the left wants to make sure that, the general on the right also knows that he has received the confirmation of the confirmation. And on and on and on it goes. And the problem is there is never common knowledge among the two generals that the other party is definitely going to attack on the next day, and that the other party has actually received all the messages. Even though they could have an infinite number of messages sent back and forth among one another, where they both confirm that they have actually received the information. So this is a problem, and this is an unsolvable problem. For those of you economists, you will have heard that in the context of common knowledge. Here in this problem, there will never be common knowledge about that both parties will be attacking at the same time. So it's a problem which cannot be solved. Now, as interesting as that might be for a network, this is not entirely the same problem, because the way we're looking at is a more general problem, right? We're looking at multiple generals. They all want to attack the city, and what they need is that a majority of the other generals attacks the city at the same time. So what you need to do is you need to have some mechanism which ensures that this attack can succeed. So how does that done? Well, the way this is done is in the following way. Now, first of all, we want to make sure to understand that here in this problem, it doesn't actually matter what they will do, right? So all that they want to do is they want to coordinate. So they want to either coordinate on not attacking, or they want to coordinate on attacking. So how can we solve this problem? Well, the first thing is we change the structure slightly. So there will be a leading general, with one on the left, looking like a general, with a lot of lieutenants. These are all the other guys there. And what he wants to do is he wants to seek the consensus time for the attack. So what this general will therefore do is he is a leader, and he proposes a time that he sends to all of his underlings, and then the underlings communicate with one another, and then they will act upon the majority decision. So here's how this looks like. So the general sends messages of the time of attack to all of his soldiers, and then the soldiers among each other send messages to discuss whether or not they want to do the attack, or there will be an attack, or rather the attack time, and they will then act on the majority decision. Yeah, so all of them see, in this particular case, it's easy. Everybody sees the attack time T, and everybody has a majority time T in their information set. Even if they don't receive all the messages, they would still be willing to do the attack at a particular time T. So that's all very well. But if you think back of the problem of attacking a city, some of these messages may be intercepted. Some of these messages, that maybe some of the lieutenants may be cowards, or they may be fraudulent. So we're looking at let's look at a more complicated model, where there's one party here on the bottom right, the guy with the sunglasses, who is actually compromised. And what will happen is that this general sends again the message T to all of his underlings. But as a next step, when all of these underlings send the messages, the cheater sends a completely different message. So he doesn't send time T, but he sends the time X. Now, do we still have consensus? So do we still agree on the right time T? Well, the answer is here, in this case, yes. And here's why. Let's just think what the messages are. So all the soldiers, the one on the bottom left, has received two messages, one from the general and one from the other party, that the time for attack will be time T. and he received a contradictory message from the cheater, which is time X. So he would still be, his majority action is still to take the attack. The same holds for the guy in the middle. And well, the guy in the corner also actually, even though he's a cheater, he actually has an information set which says that the attack time will be time t. So within this network, there is consensus and the attack will take place. Okay, so that's actually nice. And so this consensus algorithm, where you go with the majority decision, works in this case. It works, and this is a mathematical problem, unless there are 2/3, it's more than 1/3 of the network members are compromised. Now, you may ask an interesting question. You say, what happens if the general himself is actually compromised? So let's look at this example here. So the compromised portion is the guy on the top. So what this guy will do is he sends messages X, Y, and Z, so contradictory messages, to all of his different soldiers. Now, what do the soldiers do? Well, the soldiers send truthfully, so in this case, these are not cheaters, they send all the messages X, Y, and Z to their counterparties. And so now what are the information sets? Well, if you look at all of the information sets from these soldiers, they're actually all identical. Each of them gets X, Y, and Z. So in this problem, there is also consensus, except that, and this is the critical part, this consensus is here that there's a contradiction, and so you wouldn't attack. Now, this is also okay. So the important part, I mentioned that earlier, is that they coordinate. It's not important that they do a particular action. They just want to coordinate on an action. So the consensus here is the important part about it. All right. So that brings us back to the general result. So we have many generals that want to attack the city. There is an equilibrium, right? So if we have the consensus algorithm would be that you pick the majority message that you receive, and this is in fact a successful attack or a successful consensus decision that you can reach as long as no more than 1/3 of the participants cheat. And it is indeed possible that even if the leader is a cheater, that you can get consensus. What a blockchain requires in order to work, it needs to have a consensus algorithm in this distributed network that is Byzantine fault tolerant, which means that it will work unless more than 1/3 of the members of the network are compromised. Now, the trick that the blockchain technology uses and that makes this work is not just the number of messages, but it is actually really hard to forge the messages. And this is where the proof of work protocol comes in. Very handy. So now let's look at the proof of work protocol just in a nutshell. How does this work? Well, you have all of these different, Bob and Alice that have their transactions that they've signed, that they've sent to the miners. And what the miners do is they bundle these, they validate them, they put them together, and then they create a hash of this information. And now the trick for the proof of work is to find a special hash, which is the following. It is a hash of this hash, which together with a particular number, the number here is 24813, creates a hash that starts with a pre-specified number of zeros. Now, I've showed a demonstration in the last class of how this would work. So you basically take all the information, you hash the information, then you add a piece of information, do another hash, and that hash has to start with, say, 4 leading zeros, 10 leading zeros. It depends on the convention that you have. Now, that is a process which is hard and can only be solved by random guessing. So that requires time, and particularly it requires computing power. And what that creates is it creates a mechanism which makes it hard to forge a message. Now, the miners will also race to find this particular hash. And in their race, one of the things that they do is, essentially it is entirely random among the different miners as to who will be the winner of this race. Okay, so that's an important feature which we talk about later. But the important part is there's essentially a random selection out of the many miners that exist of who will be the winner. So this algorithm has the cool and critical feature is that it is Byzantine fault tolerant. And it does two things. It selects a leader and it makes messages very hard to forge. Let's skip over this presentation. But just very briefly as a summary, so how does the proof of work protocol address Byzantine fault tolerance, or why is a Byzantine fault resistant? First, the number of leading zero works as a coordination device, right? So you see a message which has this property, and then you know what to do. You know how to update. right? So this essentially, there's a message that comes to you. You can validate that this is a valid message that you want to consider. You can also validate that using basically just the hash check, whether or not this indeed is a solution which is relevant. Now, the other thing is that it's very difficult to actually create this message. So it is very difficult to forge. And so therefore, if the network would have cheating parties, these cheating parties would have to work really hard and have to expend a lot of energy in order to forge these messages and to forge them consistently. So since messages are sent to many entities, there's a strength in number. So the forger would actually need to capture all the messages, and he had to do all of the forging, which is extremely resource intensive, which he cannot do. And so that essentially then creates the resistance to a Byzantine fault, to a Byzantine attack.